Hey, my name is Wayne. I'm with Spruce Systems, working on a project called Kepler. Spruce Systems, a little background on that. We work with a lot of authentic data sharing, anything that you sign data with key pairs and you want to see that it's issued by the right party. For example, a lot of educational diplomas are going to move to digital formats that are digitally signed by universities. It's happening in the EU. A bunch of parts in the US are experimenting with it. And we're really concerned with systems that have to do with signing. And storage systems that also conform to that signing and also towards a zero trust model for storage. So I'm here today to talk to you about Kepler, which we call self-sovereign storage, and you'll soon see why this is better for user control of data, but also potentially for institutions and any kind of trusted data sharing. Kepler is a decentralized storage network organized around data buckets called orbits. Some use cases are like ensuring data replication and availability across different sites, cloud server farms, while retaining access control. Even if you don't control other clouds, if you can get other people to agree to keep certain access policies, there's no reason why we can't keep those access policies consistent. Being able to securely share data across different institutions, even if they're on different user account systems. Some legacy systems don't even base it on email. So how do you share data to people on that? Data sets, programs, build artifacts, and even external collaborators who are outside of university or institution ecosystems. So we also allow for complex permissioning systems towards zero trust. We use something called a capabilities-based permissioning system, which allows you to show up with a bunch of hall passes about what you're allowed to do, signed by the right issuers, and access storage that way. So what are orbits? These data buckets, they're defined by a so-called orbit manifest. They can live in smart contracts on blockchains, data stores with logically centered storage like Zookeeper, even Console, and it's protected by those systems guarantees. We want that censorship resistant element of it so that we can update who's in charge of the orbit. And if it's defined in a smart contract on a public blockchain, then only the user with a key can update the smart contract, including a list of what hosts are allowed to replicate the data. That's where we get self-sovereign storage from. Imagine if by your key, you could govern how your data are replicated. So the orbit manifests are used by clients and hosts to determine which hosts can be used to resolve Kepler URL. We actually skip DNS here and don't have to worry about IANA and a whole bunch of other systems because it's just defined by the orbit manifest itself, including what keys are allowed to issue what capabilities, defining the base of the permissioning system, options like consistency strategy for replication, exposed services, and different authentication methods supported. So the various actors in the ecosystem for running Kepler are the owners of the orbits that can delegate programmable capabilities. We said we work with key pairs. Well, you can use your key pair to sign a hall pass that gives someone permission to access a file at a certain path or a file of a certain checksum and manage different aspects of the orbit, everything from the content itself to configuration. The hosts are semi-trusted. Well, they're trusted by the owners to host and serve the content, but if they're not trusted at any time, the owner can eject them from the orbit by just delisting them, updating that root zone, so to speak, whether you store it in a smart contract and Zookeeper, what have you. And they are also counted on to evaluate the capabilities to make sure that they're issued by the right person. One great example is if a website says, hey, I want to store a file with you, how do I do that? If you have a Kepler system, you might say, hold on, let me write you a hall pass. You'll sign off on a hall pass to write a specific file for that web server, and the web server will countersign with their key, present it to your Kepler host. The host will check that the hall pass was correct, that it was countersigned correctly, and also that the content matches the hash. Users can use capabilities, these hall passes, to read, write, and query content, configure services, key workloads to the system, and even further delegate sub-capabilities. Capabilities are issued by the orbit owner, specify a whole bunch of permissions. So everything you need to know about what someone's allowed to do, it's contained with this hall pass they show up with. There's no role-based access control system as you might find in more traditional storage systems. This is getting us far closer to zero trust architecture because that is all the data you need to verify cryptographically to see if someone can do something or not in the system. We use a policy as code system where there's a non-Turing complete programming language. So you can imagine a set of instructions that the host has to run to actually verify if the action is authorized or not. So you might run an instruction set like step 1, check to see if the user is in the allowed list somewhere. Step 2, check who's signing for it. Step 3, make sure they're the same owner. Today, well, we work with a lot of public key infrastructure people, so that's two.
I'm sorry to cut you off, Wayne, but we've hit time.